is now going to allow us to look at some of the same sort of issues that we had looked at before, but now from a more of a system point of view as opposed to strictly a machine point of view. Now that being said, we're not going to get into true system analysis until we move on to load flow, which I think is the next topic we're going to discuss. And that's where we're going to look at systems with 5, 10, for the project, potentially even larger numbers of buses. But in Chapter 10, at least we'll have more than just generator connected to infinite bus. We'll be considering transmission effects. We'll be able to use reactive power control via excitation in combination with power factor correction using capacitances or shunt values. So we will be building upon what it is that we had done over the last couple weeks or so. While I bring up the notes, just a reminder for the quiz. So the quiz will be on April 11th, so keep that in your mind. It will be on Chapter 9 and everything before that. That's sort of a disclaimer. It's always on everything before that as well. But predominantly it's going to be focusing on Chapter 9. And you have your homeworks. Please take a look at those. Good question was asked today. Unfortunately, there weren't that many homework problems. I wanted to assign more, but there was only like 8, and a lot of them were really redundant, so I pulled out the ones that I thought were good. This Chapter 9 is one where there's fewer opportunities to do like your, give a set of numbers, generate a single number output, because a lot of the chapter is more theoretical in terms of talking about magnetic circuits and stuff. So that being said, you should spend some time reviewing the beginning of the chapter as well, because this would be a good opportunity for me to ask, a numerical part, a calculation-based part of the problem, and then maybe at the end have a little short answer talking about, what is hysteresis? Why does the hysteresis curve, what does it look like? Why does it operate that way? Why is the slope in the linear range of the hysteresis curve predominantly dependent on the reluctance of the iron core? And in the saturation region, the slope is the reluctance, or the permittivity, I should say, of air. And we spent a lot of time talking about that. Okay, so where are we now? Radial system as an example. So let's go through and let's talk about this one. So we know that this equation applies. And if we want to, we can calculate our SR value as a function of the others. So this is equation 10.2 from the book. We know, right, that SR will be equal to PR plus J times QR. That's the scalar. And we know furthermore that that's going to be the same as VR times the conjugate of I. And we know furthermore that I is right, we can use this right here and plug it in as I. And so what we end up with, after doing a couple of those substitutions, is, and another thing to realize here, we say at some point, I don't know if it's stated in the book, I don't think I drew it on this diagram, but I should have. The angle of the receiving end voltage is assumed to be 0. So that means we can count VR as a scalar, right? It simply will have a real part. 120 angle 0, 120. Okay, so SR will be equal to, and now I can just distribute some of the terms out. I need some more space. Will be equal to VR, VS conjugate, over negative JXL, and that negative comes from the fact that we're taking the conjugate of I, minus VR squared over a minus JXL. If we wanted to, we can make both of those pluses. Sorry, I'm looking at my notes. There's one thing, there's a negative sign that doesn't make any sense. Oh, okay. No. All right, that makes sense. So what we're going to do is we'll pull the, forget that for a second. We're not going to cancel those out. What we are going to do, I didn't realize what my arrows meant, is we'll pull the J's up top. And so that will get rid of the negatives, which will leave us with J times VR VS conjugate over XL minus J times VR squared over XL. That's what I did. Okay. And our VS can be substituted with an angle of VS and an angle, magnitude VS with an angle of delta. That's what we're calling it. Okay. So now continuing here. We have J times VR, magnitude of VS, over XL, with an angle of 90 minus delta. And the 90 comes from that. Right, our 90 is coming from the J. That's the 90. And it's negative delta because it's conjugate. Okay. We'll do the same thing to the next piece, which will give us a give us something that looks like this. Okay, so now, like a lot of things in this book, right, we're doing these calculations not for the sake of doing calculations. Our goal is to get to a point where we have a version of the equation that will tell us more about the way that the system works. Right, we'll make a couple of assumptions. We'll extract the elements that are important to us. We'll perhaps make, exclude certain terms. So let's split this up into the real and reactive or imaginary components. So in order to do that, apply cosine sine, and in order to make this a little bit easier, I'm going to give these names. So I'm going to call this right here, I'm going to call this alpha 2, and I'm going to call this right here alpha 1, those coefficients. So what we're left with is alpha 1 cosine of 90 degrees minus delta plus j alpha 1 sine 90 degrees minus delta minus, so the cosine of 90 degrees is going to be 0, but then we'll be left with j alpha 2 times sine of 90, which will be a 1. And then we could plug those values back in if we wanted to. Okay, so extracting these pieces, so this is the real piece right here. So PR will be equal to VR Vs magnitude over XL times sine of delta, which is the same as, this is the same as cosine of 90 minus delta, just using our good old trig identities again. The reactive part encompasses all of this. And that is going to look like, so VR, Vs over XL, cosine of delta. We'll do a similar sort of trig identity there, minus VR squared over XL. Okay, so there we split our received power into the real and imaginary or reactive components. Okay. We're going to divide both sides of the QR equation, the one that's shown right here, by this value, because it's going to make us easier to demonstrate exactly what we're going to show in 1 second. So what we're left with is QR times XL over VR squared, is equal to cosine of delta minus sorry, I missed one value. Vs cosine of delta minus 1. And so what is that we're trying to do here? Let's give a little preview for 1 second. So what we're trying to do here, and the reason why we're doing a couple of these changes, is we want to look at the voltage drop along the line. This is an important part of the way that this system works. A lot like how when we were dealing with machines, right, we were talking about the stability region in terms of how far our internal angle of the generator was getting away from the terminal angle. In this case, we're going to be worried a lot when it comes to instability about what is the voltage drop from one end of the line, or the voltage magnitude drop from one end of the line to the other. Okay, so I'll make a couple changes here. Move this.
Does the equation have a VR? Like it should be Vs over VR, divided by VR squared?
Let's see that. So Vs over VR. Where should it?
Like it should be Vs over VR cosine delta.
Ah, yes. Sorry. I'm like half copying my notes from last time. I'm half doing it off the top of my head, and so it's sometimes stuff falls in between the cracks. Okay, so we're going to add the 1 to the other side. We are going to then do something where we are going to divide by this, and we're going to divide by that. So we're going to switch the sides over because we're trying to isolate. We want to isolate this right here. So what we're going to end up with after we do this switch is we are going to end up with Vs over Vr equals cosine of delta divided by, and so we're not switching this to the other side, divided by 1 plus QR XL over VR squared. And this is equation 10.6 from the book. Okay, so this is going to lead us to our discussion. Yes?
That would be VR over Vs, right?
Sorry. I will I will look more carefully at what I'm copying. I would have caught it when we got to the next step, but you guys are faster than me, so that's good. All right. Now, so why is this important? Why are we going through all of this, this derivation right here? In power systems, or in many types of systems, but power systems especially, our goal is to maintain voltage magnitudes as close to the rated as possible. Now there's a whole wide array of reasons why that's true. Number one is because obviously that's the value at which it's designed to operate. But in addition to that, we know that the region of stability for these values is relatively small. So assuming that the generators are operating at 1 per unit, okay, which they should be, right, then we don't want our, right, that's our reference point. So any bus that strays from that enough is going to lead to instability in the system, really, really large currents flowing, similar but less so than to a short circuit, right? The reason why short circuits are dangerous is because they act as a sink for current. They draw huge currents, which causes huge drops along the different lines, and that ends up being a bad combination. So therefore, so higher transmission line loading, which means a smaller value of the load impedance, is going to correspond to higher values of delta, right? The more current that flows along that line, the more differentiation, the more phase shift there's going to be. And the reason why we're focusing more on delta as opposed to its direct effect on VR is because we're not considering the real component of the transmission line right now, right? If you go back to the circuit that we're using, for now, we're considering that that the resistive element of the line is 0. And that would change the work that we just did because, right, if we were to include a resistance here, that would give us more terms in our analysis. Okay. This equation comes from here. And so if we look at this, what can we observe? Don't worry, we're going to come back to this equation here. So this will increase with loading. This will change relatively little for our case where the r equals 0. And that means that this will be proportional to sine of delta, and for small values of sine of delta, we can just say that that's equal to delta. So how do these two equations relate to one another? 10.6 and whatever the number is for this one. This should be no surprise to anybody, right? If we're talking about a given angle, a larger value of sine will correspond to a smaller value of cosine. So if, let's say, we have one vector that looks like this, and we have another vector that has the same, well, almost the same length, looks like this, as our sine value goes up, our cosine value goes down. The absolute value of it, at least. So what does that mean? So that, and when I say that, I mean above, means that to increase PR, while maintaining okay, so now going back to our equation for QR, the one here. Equation 10.5, and that's, we've already written this, but I'll have to rewrite it again for this purpose of explanation. Okay, now, we already said a couple of times that we are going to that we're going to assume that the magnitude on either end of the line stays relatively the same For this analysis that we're doing right now, we're predominantly focusing on delta. And so we can replace Vs times Vr with a 1. They're both values very close to 1. We can also replace this with a 1. And so what we end up with is 1 over xl cosine of delta minus 1. And so this proves because you may ask, well, why does QR have to be negative? I just kind of said that, right? We didn't provide any justification for that. However, if you look at what we just did with our assumption that VSVR is equal to 1, VR squared is approximately equal to 1, then you'll see that this value here must be greater than or less than or equal to 0. Yeah.
Are you doing that in per unit? Is that what you're saying?
It's all in per unit. Yeah. It's all, exactly. Yeah. Sorry, I should have specified that. From this point on, there's going to be a really quick shift to doing almost everything in per unit. In fact, I'm pretty sure that all the problems in this, I don't know how quickly they shift over. The other book is a little bit, the Granger book, one from they referenced in the lab, goes very quickly to using all per unit. But yeah. So let me say 1 per unit, 1 per unit. So we see that this value must be less than 0. So as PR grows, so does theta. As theta grows, cosine of theta goes down, and that term that's inside the parentheses gets larger and larger, or gets more and more negative. Go ahead.
So, wait, it must be greater than, or I think it must be greater than 0.
No, less than. Yeah. Because if you think about it, what's the maximum of cosine? When you have cosine of 0, it'll be 1. You end up with 1 minus 1 equals 0. When you're at the minimum, which is cosine of 90, it'll be 0 minus 1, which will give us negative 1. So you'll never, because cosine of delta can never exceed 1, you'll never get a positive value. So what does QR being negative mean? If we go back to this figure up here, right? The direction of SR looks like that. So QR being negative means that it's actually supplying reactive power back to the system. So there's an interesting relationship there, and this is one of the things that we're trying to hit upon when we look at the power system as this mini power system as a whole, is that the more real power the load consumes, okay, the more reactive power, or the more negative reactive power, right, or the more reactive power it has to supply back into the system. And the reason for that is because we're assuming that Vs is approximately equal to Vr. Okay, if we didn't make that assumption, this wouldn't hold true. That reactive power being supplied by the receiving end is essential to propping up the voltage magnitude at the receiving end. Otherwise, there would be a pretty significant drop along the line. Okay. So, you guys give me 2 seconds break. I want to pull up another set of notes because I feel like my explanation here, I might have skipped something. So take a 30-second break. Chris, let me see your book one more time. Thanks. Okay. So, okay, so now let's talk a little bit about what's happening at the sending end. Okay, we know that QS must be equal to negative QR. Okay, and that's because if we look all the way up here, our direction of SS is as such. I gotta start bringing this book to class. Okay. And so if QR is less than 0, then QS has got to be greater than 0. Both sides supply equal reactive power to the system because they have the same voltage magnitude. And what this means also the generator must operate in the overexcited mode. So what's happening to QS and QR? It's being stored in the line inductance. XL. All right, that brings us pretty close to section 4.6, which will build off of this